Well, welcome to part 2 of our triangle bisector section. And in this section, we're going to talk more about the intersection of angle bisectors. Our last section, we talked about perpendicular bisectors. And so this section, we're going to focus more on the angle bisectors and different terms that we're going to have, new terms that refer to angle bisectors. So anyway, we talked about the point of concurrency of perpendicular bisectors, and in this lesson we're going to talk about that same point of concurrency, only it's for the angle bisectors. And it has a special name, and the name of that term is called the incenter of the triangle. So in this example, point P would be the incenter of the triangle, and the incenter is always inside the triangle. Alright, so in this diagram we have points X, Y, and Z are equidistant from the incenter P of the triangle, and P is in the center of the circle that is inscribed in the triangle. So that's different from what we had in the last section. Remember the last section, the triangle was circumscribed, it was inside the circle. This time we have the triangle on the outside and the circle on the inside. So they're exactly the opposite of what we had the last time. So our theorem for concurrency of angle bisectors says that if we have three angle bisectors, okay, so you see each of these angle bisectors here, we have AP, BP, and CP, and they are concurrent at point P, that means they intersect at point P, then this theorem says that that point of concurrency, or the incenter, is equidistant from each of the sides of the triangle. So the blue dotted segments indicate that those segments are equal distance or equidistant from point P. So let's go ahead and use that to figure out some problems here. In this example, we have triangle ABC, and they give us some algebraic expressions for segment GE and GF and want us to find the length of GD. Okay? So we have an expression for GE and for GF, and we're looking for GD, the length of GD. So first of all, we need to recognize that we do have three angle bisectors here intersecting at point G. So we say that G is the incenter of triangle ABC because it's the point of concurrency of all the angle bisectors. So therefore, we know that from our last theorem that we just talked about, the distance from G to F, G to E, and G to E are all equal. So we can go ahead and set GE equal to GF because they are both equidistant. So substituting our algebraic expressions, we get this. And then if we just go ahead and add 7 to both sides, we get 2x equals x plus 11. And then subtract x from both sides. That gives us x equal to 11. But that's not what we want. That's going to help us get to what we want, but that's not the answer we're looking for. So we can find either GE or GF. They chose to find GF, so let's substitute 11 back into the expression x plus 4. That gives us segment GF has a distance of 15, or a length of 15. And since they are all congruent, we know that GD then has a length of 15 as well. Here's an opportunity for you to try to solve a problem similar to the one we just did. Go ahead and pause the video, and I will give you your answers when you come back. All right, let's take a look at this example. We have, very similar to the last situation, point Q is an angle bisector, okay? So it's bisecting angle K and angle L are being bisected. So we can find the incenter just by getting the two angle bisectors, even though the third one is not given. We know that they would intersect at the same point. So Q is definitely still the incenter. So then we know that OQ, NQ, and MQ all have the same length. Well, our expression, we have QN and QM, and we know that those are going to be congruent or equal in measure. So we can go ahead and set them equal. We can say 5x plus 36 must equal 2x plus 51. And then we can go ahead and subtract 2x from both sides. If I go minus 2x on both sides, minus 2x. then we get 3x, this is really hard to draw straight lines on this thing, 3x plus 36 is equal to 51. So lastly, we can subtract 36 from both sides, minus 36, and these cancel, and we get 3x, I'm going to continue over here, is equal to, what does that give us? 15. So we know that x equals 5. But that's not what we were looking for. But that gets us on the way, right? We're looking for the distance from Q to O. So we can substitute 5 back into either one of these expressions. If there's one that's easier to work with than the other, I'll just substitute it into QM. And we get QM. Let me choose a different color for this. QM is equal to 2 times 5 plus 51. So that's equal to 10 plus 51, which is 61. Okay, and QO is equal to QM, so QO is also equal to 61 units long. Now, the second part of this question says, is it possible for QP to equal 50 and explain? Well, 50 is smaller than 61. And 61 is the shortest distance. Remember we talked about that in one of our previous lessons, that the shortest distance from any point to the side of a triangle is the perpendicular distance. It's along that perpendicular bisector or along the perpendicular line. And so no, it is not possible to have that distance be shorter than the perpendicular distance. All right, here's your lesson check. Go ahead and work on this and have this ready to turn in tomorrow, and we'll see you then.